introduce Dimitar Grantcharov from UT Arlington. Please take it away.
Thank you. Thanks a lot for the invitation. I hope all of you are doing fine. Thanks for coming. Uh, my talk will be Lie algebra representation theory talk, but since it is on the first example of non-trivial Lie algebra SL2, I hope it will be understood from a broader by a broader audience. This is a joint talk with Nguyen and K Zhao. It is a project which will result in two papers and hopefully post it soon. This talk will address parts of both papers. Feel free to interrupt me anytime if you have questions. Again, I will try to make it more accessible. On the slides, you can see some technical notions that will distract you probably because of the many formulas. I will try to explain what is going on in some general terms so that you understand better. Let me start with the setting. The ground field will be the complex numbers all the time. We will focus on SL2, the three-dimensional complex Lie algebra, most of the talk. But in the beginning, I will mention a few general facts and definitions, results mostly on arbitrary, simple, finite-dimensional complex Lie algebras. And what you need to somehow remember, H will stand for a fixed Cartan subalgebra. In SL2, this is one-dimensional subalgebra, which will be simply the diagonal matrices of SL2. SL2 are the traceless 2 by 2 matrices. So it's kind of the diagonal matrices of the form A00 minus A. U of A will stand for the universal enveloping algebra of A. A is again arbitrarily algebra, although most of the talk it will be SL2. So I will start with the notion that will not be of interest for this talk and our project. Weight modules are modules that are relatively well understood. So let me tell you in advance what will be on the next paragraph. We do have a classification of simple objects in this category for certain kind of ingredients. More precisely, if we consider S, this S here is a simple finite dimensional complex Lie algebra. And we consider modules that are direct sum of their weight spaces. This M lambda is a weight space. And if in addition, this green thing, we ask the weight spaces to be finite dimensional, then these weight modules of finite type are in a way understood on the level of simple objects. We do have a classification of simple weight modules of finite type over S. But what is important about the weight modules is that each element of the Cartan, small h, acts semi-simply, or let's say locally semi-simply on the module. We can extend this notion to, instead of semi-simply acting with a Jordan cell, this will normally refer as a generalized weight module. So a simple generalized weight module is a simple weight module. So in a way, the simple objects of finite type, when H acts, say, locally finitely, these are well understood due to a famous result by Olivier Mathieu in 2000, who used previous works of Bankert, Britton, Fernando, Futorni, Lemire, and others, and he completed this classification of simple weight modules. We will mention, if the time permits, a few parts of this classification. He heavily, not heavily, but he introduces the notion of coherent family, which plays major role in this classification. So this is a huge weight module, somehow containing both highest weight modules and modules that were not previously classified, so-called cuspidal modules. So somehow Mathieu put everything in one big family, and somehow understanding one part of the family leads to understanding the other part. This is very roughly, very roughly what is going on in this classification. We will not refer to it again. Our goal is to look at another part of the representation theory. It's more like the opposite spectrum of this set of problems. Instead of finite action of H, we look at free action. So the opposite to finite is more like torsion free, but we will start with the easiest torsion-free action, the purely free. So we will look at modules that are free over U of H, more precisely as this isomorphism states. We look at modules that are direct sum of U of H, finite direct sum when restricted to U of H. And again, we're using this kind of general fact that a module over the Lie algebra is a module over the enveloping Lie algebra, and U of H, H being a abelian Lie algebra, is nothing else but C of H. So you will hear this C of H a lot. C of H stands for the polynomial algebra in our case of one variable, because H, the Cartan of SL2, is one-dimensional. And again, our goal is to study as much as we can S modules of finite rank, which are free over U of H. Now, before we continue, a word of warning. There is certainly a result on the classification of all simple SL2 modules. This is a famous result in the 80s of last century by Richard Bloch. Unfortunately, this classification is very abstract, and it doesn't give any parametrization or classification in terms of some sets, or at least even saying to what extent is wild. So one side goal of the talk today is to convince you that this problem of discussing in more detail Bloch's classification is probably out of reach. So today we will talk a lot on rank 2. Rank 1 is well understood. And again, we talk about UH3 modules of rank 2, and still we have a huge family of modules, and simple modules to be precise. So this was kind of the preliminaries. Now we will start with the real stuff. Any questions? So a few remarks here on the relation between weight modules and, say, free modules. There is a connection that initially can give you a lot of hopes that understanding weight modules will lead to understanding free modules. By free, I mean UH free. And this is due to this weighting functor, which appears first in a paper of Nielsen. Nielsen credits Mathieu for the idea. It is a functor that somehow makes weight spaces, and as a result produces a weight module. If M itself is a weight module, this W of M is simply isomorphic to M. But if M is a free module, UH free module, then W of M is a coherent family. It is a huge, huge weight module with what we call support, the set of weights, like the whole Cartan to some power. And let's put here one example that's kind of a famous presentation of the Lie algebra SL2. So I'm using this slide to mention that EFH will stand for the three generators of SL2. We will introduce them more officially on the next slide in terms of matrices. And this is an example where we have like a homomorphism from the universal enveloping algebra of SL2 to the first, say, Weil algebra, the algebra of differential operators of one variable T polynomial differential operators. And we have, for example, the polynomials as a module over SL2 in a nice way. So this is a weight module. We can kind of twist CT with some powers of T, and we get some important weight modules that will lead eventually to the classification of all simple weight modules of SL2. But if we use exponential, and now this E is certainly not this E, this is like exponential of G. This is a non-weight module. In fact, it is a free module. And if G is of degree n, G is a polynomial of one variable, degree n, this will lead to a free module of rank n. And this will be discussed again later. It's interesting to know that if we have, for example, degree 2, this module is simple. I think this is can be generalized for degree n. Again, I will mention this later in more detail. This is something which we're absolutely sure about. And also, I want to mention that there are more presentations of SL2 in terms of differential operators, essentially different, right? Here, E and F are kind of operators of, say, how to count this, like uh, uh, degree 0 in T, degree 1 in D, and so on. But we have a presentation where E is like degree 1 in T, degree 0 in D, and so on. So we have several presentations, and this is some very, very primitive version of D-module theory. But yet, the important part is that different presentations of SL2 in terms of differential operators give you different exponential modules and hence different UH3 modules. So we have something like 3 families or 4 families of exponential modules. And for one of them, we still don't know whether the corresponding modules are simple. So this is how kind of the theory comes in the very simple case SL2. We have some natural open questions, and now I see that the last line of the slide is not probably visible. Let me see for a moment if I exit the, yes, if I exit the full screen mode, you can see the last line is saying that the weighting functor of EGA results in a coherent family of degree n. Okay, so now the precise definitions. So these are the 3 elements of SL2 that will be used. H is a bit non-standard. H is normally 1, 0, 0, minus 1, but we pick this particular basis element of the Cartan because we really like this definition, this relation, H E bracket equals E, because with this relation, the important automorphism for the polynomial algebra of H looks better. So we have one shift that will play crucial role in all considerations. And the shift is H maps to H minus 1 in this setting. And if we have 1 minus 1 here, it will result to 2e here instead of e, and the shift will have to be H maps to H minus 2. Not that it is bad, but one has to involve these two all the time. So sometimes powers of two appear, and we certainly prefer powers of one. This was the setting that Nielsen used in his paper on the study of rank one modules. So in a way, it is also nice to somehow follow his notation, since we will refer to his classification later. So then the center of the universal enveloping algebra of SL2 is generated by one element. We pick this particular element in our talk here, small c. Again, we identify all the time u of h with c of h, and this sigma is very important. So sigma throughout the talk will be the automorphism, which is shift like to the left, sigma of h. And then we have n by n matrices forming a group. And as you know, this is the unpleasant part, since the entries are polynomial. To have a group of matrices of polynomials, the determinant should be non-zero scalar. So this group is kind of restrictive and definitely difficult to work with. And now again, I see that one part of the last sentence is not visible. I will mention it. So the similarity of matrices that plays crucial role in linear algebra, right? We for example want to study n by n matrices with complex numbers. We have Jordan canonical form, and we have that every matrix is similar to Jordan canonical form matrix. So the whole point is that in the SL2 representation theory, if we have like H3 modules, the important notion is sigma similarity, and this leads to a lot of problems. So of course, sigma similarity and regular similarity coincide if we consider just scalars here. But this is the condition for sigma similarity, and this condition appears a lot when isomorphism theorems are kind of considered, studied, obtained. So instead of regular similarity, we need to study sigma similarity, and the condition when two matrices are sigma similar is easy to write, but difficult to work with. So if I give you two matrices and I ask you check if they're sigma similar, you will have very hard time obtaining the answer, and especially if n is at least 3. So this is part of the main topic in a way, that n equals 2 is uh, easier to handle because of some results for the group GL2CH. But n bigger or equal 3 is very difficult to handle because it's very hard to work with conditions like this. And on the bottom line, it says, similarly, we define sigma inverse similarity. So we have sigma similar and sigma inverse. Sigma inverse is with h plus 1. And if two matrices are sigma similar, certainly we don't have that they're sigma inverse similar. Okay. So we move to the definition of this module MEF. So I will slow down a bit because now we have formulas and new letters. So this lemma gives us a nice description of all SO2 modules that are free over CH of rank n. So one would say, oh, our job is done. Just a remark. So this is not done for two reasons. We need isomorphism theorem and we need better description, right? So the first lemma will be in terms of two matrices E and F. And also on top of that, like second, the simplicity question remains the most difficult question. Like for which E and F, this is a simple module. So anyway, let's continue. We start with this condition. So that's very important. In all considerations, we require the underlying space of the representation of M to be direct sum of n copies of the ring C of H or the space C of H. And H, small h, acts as a multiplication. So in a way, we want to see what happens with the action of E and F, right? And when I say EFH, I always will refer to this EFH. So how does small e act? Small e act by a matrix E. But in addition, we need this sigma. Once again, this sigma is super important, right? The shift. And then also for F, we have the same thing. We have a matrix F, n by n, and now we need sigma inverse. As I mentioned, H acts by a multiplication by a scalar. This sigma and sigma inverse easily follow by this condition and this condition. So it's not a surprise. But EF minus FE equals 2H will give you this matrix equation, which is not very pleasant, right? So you cannot say that if we have E, we easily find F. It doesn't work like that. So luckily, for matrices, we still have this Smith normal form. Okay, so Smith normal form is not like Jordan canonical form, but it is still some reduction that can be used and make this identity and more kind of pleasing. So because now we are saying that the module depends on two matrices, but these are not free choices. I mean, we cannot just choose two matrices. They are subject to this condition. So if we implement this Smith normal form, we have a better condition. But before that, and I need to again switch to regular mode. Before that, immediate lemma about the isomorphism theorem. If we have isomorphism of two modules with E and F, we need sigma similarity for the corresponding E matrices and F matrices. So that's not a difficult question to answer here, but again, it's difficult to work with explicitly when we have concrete matrices. So how does this Smith normal form helps? If we start with a module with fixed central character, and to this central character, we can associate alpha or vice versa. We will start with alpha, which will result in a fixed central character. Then, after finding the Smith normal form of F, which is exactly this matrix here with mu i's on the diagonal and zeros everywhere, the module depends on alpha, the mu's, and this matrix K, which is element of GLN. And these mu's, by the Smith normal form, are related that the one on the top left divides the one on the kind of bottom right and so on. So these mu i's, like Smith normal form, phenomena. Mu1 divides mu2, mu2 divides mu3, etc. These xi's are related to mui's through the central character. More precisely, we have this condition. So we have one special polynomial, which we denote by lambda alpha. In a way, you can think that this polynomial is polynomialization of the central character, right? Because central character and this, they look very similar to each other. Of course, we have polynomial degree 2 here, but the point is that we still need more refinement. It's not like gamma determines alpha uniquely. I mean, it's obvious that it's not the case. We may have two alphas, but the problem is that the two alphas giving the same gamma, they still give us non-isomorphic modules MEF. So with this setting, um, maybe I should not show the remark at the point. With this setting, we have again mui's, which determine uniquely xi's, alpha, like almost the central character, and this kh, an n by n invertible matrix, not invertible to be precise, element of GON. Because determinant non-zero is in a way invertible, but then the inverse is not necessarily a matrix of polynomials. It can be a matrix of rational functions. So element of GON, mus, and alpha. And then here is the kind of the technical remark. If you want to ask what are exactly these elements K, mu in terms of Smith normal form. So if the Smith normal form again is the mui's, then you have this PHFQH, and K is nothing else but Q inverse P inverse, like this matrices of transition to the Smith normal form. So an SNFF, this is exactly the mui's. Okay, so then we can go to the next slide, which is a bit technical. So let me just tell you what you see here with so many indices and letters. First of all, the idea is to give a parameterization of this MEF. And as I mentioned, we have A, alpha, and K involved. It's good to put A and alpha together and form this polynomial PA alpha H. And this polynomial is more like a matrix of polynomials. So this is precisely what is on the mu_i. So this PA alpha H is nothing else but this matrix here. But you also put alpha in the picture because the mu_i's are at the end of the day divisors of this degree 2 polynomial. So mu_i and of course xi is either degree 1 or this polynomial or this or the whole polynomial of degree 2. So mu_i is of degree 0, 1 or 2, and degree 1 has two cases. So for this reason, it's good to introduce like a triple of integer constants where you count how many we have of degree 0, how many of degree 1, and how many of degree 2. And degree 1 could be one or the other. That's why in the middle we allow integer numbers. So this is not like some fancy choice. As it will be seen at the end, this choice in a way gives us a nice relation with the weighting functor. So it's good to allow the second invariant to be integer. Somehow say for this you put positive number, for this negative, and in this way again you identify the matrix in the middle, which will be PA alpha H. But if you know A and alpha, you immediately can say what this is. So the most pleasant case will be if all have the same degree. And this is the case when it is a scalar matrix. And this will be called scalar free module. And these are the modules we completely understand. If we have different degrees, if uh, more than one of these guys is non-zero, then we still have open questions. I mean, essentially the simplistic question remains open. So back to the kind of the setting, immediately isomorphism theorem here between two modules is a bit technical, but again, the corresponding case should be sigma similar, but this is not sufficient even if you assume that they're equal. The relation between A alpha B beta is kind of a vile group relation, and somehow the B, which here is not visible, keeps the A's as they are, but it puts negative number. I mean, it's which is A0. So this is for the for the isomorphism, and in a way from now on we want to study these modules. And again, this is a module with fixed central character, so we make our life easier by fixing the action of the center. So we start with the theorem, which I attribute to our joint work, but I should mention that there is a work of Futorni, Lopez Mendonca, I hope I pronounce the names correctly, where this was also considered, this type of exponential modules. So this proposition is easy check. I'm just kind of preparing you with the notation. So this one n minus 1, 0 means we have one element, mu1 of degree 0, n minus 1 elements of degree 1, and then this matrix, which appears in the paper of the three authors I mentioned, Futorni, Lopez, Mendonca, and they have this companion matrix. So it's kind of very, very similar. And K of H is not exactly companion matrix. So it's interesting to make some kind of vocabulary one setting to the other. But this goes back to kind of the exponential module construction, how the exponential module looks like in our language. Now, the first work on the subject by Nielsen, who classifies all rank 1 UH3 modules, and he classifies which ones are simple. So again, we know that all modules are of this type, but let's see what are the simple ones. First of all, rank 1 means that the sum of these guys is 1. So like 2 zeros, 1, 1. And if we have degree 0 or degree 2, then the modules are always simple. But if it happens that we have degree 1, like half of them are simple, and here you can see how important alpha is. So all these guys are with the same central character, but if you pick a particular alpha, and this is regular integral central character, if you pick this particular alpha, this is not simple. And it is kind of interesting extension of a finite dimensional module. This is a finite dimensional module, by the way, a module of highest weight to alpha minus 1, which is non-negative number, and another UH3 module of rank 1. So this guy is simple, this guy is not. So in a way, you relate this case to this case, and the answer is we have more like extension of the corresponding other alpha with the same central character with finite dimensional module, which explains how complicated this category is. So the category of weight modules is very nice because quotients of weight modules is weight module, submodule of weight module is weight module, while the UH3 modules is non-abelian category, right? You have this quotient that I highlighted, and this is finite dimensional. So that's not a surprise, but it reminds us that if we even dare to finish the kind of question on simplicity, the next question will be even more complicated, like what about in decomposable? So we have natural extensions between weight modules and UH3 modules. And with this in mind, again, this is Nielsen's classification revised. Now we switch to rank 2. And that's like a complete change of considerations. Like we're going to a different world because now we need some theory of GL2CH of this group. And the paper that helped us a lot was a paper of Kohn from 1966. So this is like 60-year-old paper. And it is providing a decomposition of an element of GL2CH into a product of special matrices, and these matrices are these matrices. The important part about this decomposition is we have a nice uniqueness theorem. So we have different decompositions, but no matter how nice they are, we don't get this nice uniqueness. And that's why we like this result of Kohn because of the uniqueness. The price we pay is that our elementary matrices, in a way, the ones that we build the decomposition on, are of this type. So these are matrices with determinants 1, right? U of h itself is arbitrary polynomial, and so challenge. Here is one of our main results in the rank 2 paper. And this is simplicity for scalar modules. So that's very important. Now I emphasize on this type, which in our setting is this, which again results in these matrices mu i's being a scalar types identity. Why is this nice? Because in these cases, the matrices for F and E are scalars types, scalar matrices times element of GL2. And again, for GL2, we can apply, and it is not trivial application, but we can apply, work with, and take advantage of Kohn's result. So Kohn's results in very rough forms is that every matrix in GL2 is a product of a diagonal matrix and matrices E of UI. And he has included a few conditions, like the first and the last of these UIs are arbitrary, and everything in between is here. So we kind of give a theorem that provides a nice necessary and sufficient condition for simplicity. of again scalar modules. But again, this is sigma similarity. It is not the explicit uh, uh, theorem we want. So in our defense, we do have explicit theorem, namely we do say when a matrix is similar to this, but it results into 7 cases, and they are not that pleasant here, and no one would benefit if I just give you the 7 cases. They're in a way symmetric, symmetric cases, but uh, in a very special way. So, first of all, the question is when is a matrix sigma similar to diagonal? I mean, this is a bit more, and if you understand this seemingly innocent question, you will understand the general question. But when is a matrix sigma similar to diagonal matrix, that's pretty tough. I mean, that turned out to be a very non-trivial question, and again, it results to 7 cases. And in these cases, one may think of the following general idea that appears in all 7 cases, like U1 is sigma inverse similar to UK with some deformation, U2 to UK minus 1, and so on. And in this case, we have a non-simple module, right? So if we have sigma similar to diagonal, the module is not simple. So in a way, when the module is simple, answer when it is not sigma similar to diagonal. And here we have a lot of cases. And of course, again, we need to split the consideration into 2 parts, like in Nielsen. But just let's stop for a minute and see how complex the situation is. Rank 2, scalar type, SO2, UH3 modules, like part of a part of a part of the theory, leads to a huge family of simple modules. Namely, we fix alpha, we have 3 cases of A, and then we have two more parameters, A and B, I mean, non-zero complex numbers, and then a sequence, a finite sequence of polynomials. So it's not like one polynomial, a finite sequence of polynomials. And this will give you a simple module. So this is how bad the things are. You try to parameterize, you have some parameter like obvious roughly central character, some discrete parameter, two non-zero uh, parameters, non-complex numbers, and then a set of polynomials. Okay, and again, this is one of the easiest cases. So with this in mind, a few remarks. So Kahn's paper is again from 66, and we, as I mentioned, we explore similarity to diagonal matrix, and this is quite non-trivial. If we go beyond the scalar type, which means the 2 degrees are different, we still don't know when the module is simple. And I collected 5 results, previous results uh, on the subject. They are not ordered alphabetically or historically. It's more like a rank 1 versus a rank n versus a rank 2 versus exponential versus exponential. And this is the paper of Tornio Lopez Mendonca that I mentioned. I'm missing a comma here. I'm so sorry. Of course, these are 2 names. And so just to point out, all of them are modules of this form, and these are not scalar type. So this scalar type that we reviewed is part of some of these papers, and many of these papers answer some simplicity question for some specific family. Normally, you have one polynomial involved in the kind of family of modules that you consider. And once again, for our case, we have like a finite set of polynomials. This is how complicated the subject is. So the remaining part of the talk will be more kind of representation theory oriented to people who like weight modules. So maybe you're tired, and I apologize if I will kind of attack you with more notation. But this is normally a question asked by experts in weight modules. My like big part of my career was devoted to weight modules, so I'm biased here to kind of refer to this myself. So what is the weighting of MAK? The, this is part of our other paper. So again, we have a paper on general properties of MAK, these modules, and we have a paper on scalar UH-free modules of rank 2. So the weighting of MAK is, as I mentioned, a coherent family, and the family will be some kind of the size of this A. So it will be of rank A0 plus A plus A minus, and A0 should be with absolute value. So the four families involved in the description of these coherent families. So I will give you explicitly like four coherent families of degree 1. And then MAK will decompose as direct sum of some of these four families. So this is a quite famous family. This can be uh, explained as F injective family, some kind of twisted localization of a highest weight module, E highest weight module. So we take advantage of the injective action of F. Once again, this is a huge module. You can see V lambda is like a space parameterized by a complex number. So, for example, if you take lambda to be integer, this will be a submodule of the whole family. So the family contains a lot of modules. So it's like a direct sum of modules, and this direct sum is like uncountable. And this F minus somehow stands for like the minus, the negative root element acts injectively. Then we have one special family where both E and F are not injective, so they do have kernels. This, in a way, is related to a representation in terms of differential operators that I gave earlier. So, but you can give a differential operator presentation of this family. And then if you switch the action of E and F, let's say through this Chevrolet automorphism, it goes to, or take the negative transposed, or kind of either way. So you have a nice switch of action of E and F. This will result in two more families. So if you switch the action of E and F through, say, the automorphism negative transposed, then E will act injectively. And here, again, you will have some switch, which in a way can be explained with changing alpha, but that's another thing. But let's just put that we have two more families, which I denote naturally by F plus and F0 plus. So F0 plus can be explained with another F0 minus when you need to change alpha, but it's good to keep F0 plus for the upcoming theorem. So once you have this, so the best result is kind of here. So here is the result. So the weighting functor, you see how nice the parameterization of this module comes. A minus A0, A plus comes, they come as multiplicities of the corresponding families. So in a way, one reason to parameterize our module with these A's. Okay, and the last thing I want to mention is the Sokal filtration of the modules um, and in the composability. So these modules are not simple, certainly because if this matrix is upper triangular, it is very easy to notice that the module is not simple, but we have a natural Sokal filtration. These are rank 1 free modules. We discussed the case of Jordan cell because this is an interesting case when we will have possibly indecomposability. If this is identity matrix, then it is easy to see, or diagonal matrix, it's easy to see that this is direct sum of modules. But it's good to see the structure of this when we have some extensions. So in the first natural non-trivial case, Jordan cell, we have this nice Sokal filtration. So each of the layers is a direct sum of rank 1 modules. And here is in the composability situation for two specific cases. We still don't know. Probably someone knows, but we still don't know in general what the in the composability answer is for arbitrary and arbitrary A. But for n equals 2 and 3, we know. And again, uh, the composability for scalar type is easy. Once we go out of the scalar type, we have some kind of indecomposable. And one may think, oh, then probably only the scalar type are the decomposable. For n equals 3, you can see like if we have 2 of degree 0, 1 of degree 1, this is decomposable. So it's kind of an interesting case on its own, how these modules decompose into modules of lower rank. And again, on the simplicity level, we don't know yet, even for all rank 2, but we hope we will get soon. For the non-simplicity, we have some natural question and still a lot of open questions. And that was all. Thank you very much.
Thank you very much for the very nice talk. Are there any questions for Dimitar?
I see my co-author is here. If I make any mistake, please
Hi,
let me know.
Dimitar.
Hey.
Yeah, this is Kaiming. Yeah.
Yes, I saw you
Uh,
clapping here, and
Hi,
nice
hi.
to see you.
Yeah, nice to see you here. So let me see. Um, is it known all the incomposable weight SR2 modules?
Wait. Um, yes, yes, because they're bounded. Um, so, yeah,
Uh-huh.
good question. The best reference probably is Mazurchuk's book. He has some kind of description. So the we have two categories: weight and generalized weight modules.
Yeah.
Yeah, and for the generalized weight modules, the answer is wild. So I mean, we do know all modules, but it's about category.
uh, okay. So for weight modules, incomposable are all weight multiplicity one or not? It should
The
be not.
simple weight modules
No,
of
no, I don't.
SL2
No,
have
no,
weight
not
multiplicity.
simple. Indecomposable.
We do have indecomposable of higher weight. So we do have extension of two weight modules of weight multiplicities one, which is still a weight module. So we
Sorry, sorry. I have another question. Sorry. Thank
sure.
you. The similarity, sigma similarity over the one variable polynomial ring. So if for the ordinary similarity, do we know any
W-
good results on that?
On which similarity?
The Euro similarity over one variable polynomial algebra.
No, I think we discussed that. You probably know better. So
Not better. It's a good
we
question. So
can,
we don't have
I
canonical forms. Yeah.
I
Even
don't
mm,
think so. I think I asked you the same question years ago. Yeah.
mm, okay.
So
Yeah,
that's
yeah, yeah. Thank you. I think
thank you,
leave
Jaime.
the time for other people to ask. Yeah, thank you.
Okay, thanks.
Any other questions? I'm wondering if you restrict to the modules that come from differential operators, if there's anything nicer that you can say, for example, maybe relating to like representation theory of the Witt algebra or the Weil algebra or something like that.
So that's a very good question. I will try to answer shortly because I really like this question. Let's say we have three levels of questions on the H3 module. So we consider modules which are H3, and we have SL2 question. We have question over the first Weil algebra, but then the free action should be over T DDT, right? T DDT should be the kind of the replacement of Cartan. And then we have some kind of intermediate question for the orthosymplectic algebra. And if we have to rank the difficulty, SL2 is the hardest, OSP is the intermediate, and the Weil algebra is the easiest. And the point is how many non-scalar type do we have? For scalar type, we have a nice result due to decomposition. For SL2, we have three non-scalar type, kind of depending what the degree of mu1 and mu2 are. For D1, for the first Weil algebra, we have like only one. So in a way, we hope that for the Weil algebra rank 2, H3 modules, H being the algebra generated by TDT, we will get it first. And OSP 2, I think we have two only. So it's interesting level of difficulty which goes on and on. But we have certainly how to say fewer D modules, fewer algebra modules which are H3 than SL2 modules, simply because with certain correspondence, a module over the Weil algebra will be a module over SL2.
Thanks. Yeah, that's very interesting.
Mhm.
Any other questions for this? Oh, there's a question in the chat. Have you identified a necessary property that the coherent family Wm must satisfy if M is simple?
So first of all, I hope I didn't mispronounce your name. Is it Mendonca? I I'm sorry. I mean, I should have I should have done my homework. So, and congratulations for the great paper. Now, if M is simple, what is W of N? Uh, that's a great question. I think, first of all, I don't know. The answer is we haven't identified unnecessary, not necessary and sufficient. Oh, yeah, even necessary. That's a great question. I think I have thought for a moment about this, and the point is let me go here. Uh, I'm afraid that it will be an unpleasant answer. Somehow, we have too many modules that are staying above one family. It's like a huge set of modules. So most likely the condition will be on K, but varying K, we will have the same family. So
Yeah,
it will be
sorry to
probably
interrupt.
possible. Hmm?
Yeah, I think the answer say uh, generally for our modules, WM will not be simple. That is my
Sure.
yeah. So if M
Uh,
is simple, then you get just
I see.
dimension one weight modules.
Yes.
So that is generally you
Correct.
say our modules, say the rank is two. That means the weight multiplicity is two. Then it's always non-simple. The weight module is always non-simple. Yeah,
Uh,
because the simple weight modules are always multiplicity one.
that is correct. Yes. Yeah, I was thinking for something else.
Oh,
Um,
sorry. Sorry.
no, no, you're absolutely right. Yeah, we can define some kind of we try the generalize coherent family where we may have like instead of weight module we have generalized weight module, and then we may have some kind of indecomposability there. But the problem is, I mean, the general warning is the weighting functor kills a lot. So you see, out of this huge family, out of this huge set of modules that depends on arbitrary matrix, this matrix disappears on the right when we take the weighting functor. So we lose a lot of information with this weighting functor. That was our original goal. Maybe the weighting functor is a key for success, and we have some kind of a reverse functor, and this is out of reach. I mean, a weighting functor is like huge smashing of this set. So in a way, whatever you ask here for the weighting functor, probably it gives you some idea like this, but very rough. Later questions will not be able, I mean, you will not be able to answer. But thanks, Kaiming, you're absolutely correct. I mean,
Are there any questions for the speaker? Okay, if there are no other questions, then let's thank him once again.
thank you.
Thank you. Yeah. Bye-bye.